Welcome to our physics lesson on Stokes Law and Terminal Velocity. This is an important topic in fluid dynamics that appears in Class 11 physics for CBSE and NIOS curricula. Have you ever watched leaves falling from trees or observed dust particles settling in a sunbeam? If so, you've witnessed terminal velocity in action. When objects fall through fluids like air or water, they eventually reach a constant speed called the terminal velocity. To understand terminal velocity, we need to first understand the forces acting on an object falling through a fluid. Let's consider a small spherical object falling through a viscous fluid like water or glycerin. There are three main forces acting on this sphere. First, the weight of the sphere, which pulls it downward due to gravity. Second, the buoyant force, which pushes the sphere upward. And third, the viscous drag force, which opposes the motion and also acts upward. Let's focus on the drag force. For a small sphere moving slowly through a viscous fluid, the drag force is given by Stokes' law. Stokes' law states that the drag force is equal to 6 pi times eta, the fluid viscosity, times r, the radius of the sphere, times v, the velocity of the sphere. It's important to note that Stokes' law is valid only when the flow around the sphere is laminar, which occurs at low Reynolds numbers, much less than 1. Now, let's understand the concept of terminal velocity. When we first release an object in a fluid, it accelerates downward due to gravity. As it speeds up, the drag force increases. Eventually, the sum of the drag force and buoyant force exactly balances the weight, resulting in zero net force and constant velocity. This constant velocity is called the terminal velocity. Now, let's derive the expression for terminal velocity. At terminal velocity, the net force on the object is 0. This means the weight minus the buoyant force minus the drag force equals 0. The weight is mass times gravity, which we can write as the density of the sphere times its volume times g. For a sphere, the volume is 4/3 pi, r cubed. The buoyant force is the weight of the displaced fluid, which is the density of the fluid times the volume of the sphere times g. And the drag force from Stokes' law is 6 pi eta rv. Now, let's substitute these expressions into our force balance equation. We get rho sub s times v times g minus rho sub f times v times g minus 6 pi eta rv sub t equals 0. Rearranging this equation, we get rho sub s minus rho sub f times v times g equals 6 pi eta rv sub t. Substituting the volume of the sphere, we get rho sub s minus rho sub f times 4/3 pi. R cubed times g equals 6 pi eta rv sub t. Solving for v sub t, we get v sub t equals the quantity rho sub s minus rho sub f times 4/3 pi, r cubed times g, divided by 6 pi eta r. Simplifying this expression, we get our final formula. V sub t equals 2 r squared times rho sub s minus rho sub f times g divided by 9 eta. Let's understand what this formula tells us. The terminal velocity is proportional to the square of the radius. This means if we double the radius, the terminal velocity increases by a factor of 4. The terminal velocity is directly proportional to the density difference between the sphere and the fluid. The greater this difference, the faster the sphere will fall. The terminal velocity is inversely proportional to the viscosity of the fluid. In more viscous fluids like honey, objects fall more slowly than in less viscous fluids like water. Let's work through a numerical example. Consider a small steel ball bearing with radius 1 millimeter and density 7,800 kilograms per cubic meter falling through glycerin, which has a density of 1,260 kilograms per cubic meter and a viscosity of 1.4 Pascal seconds. Using our formula, we can calculate the terminal velocity. V sub t equals 2 times r squared times rho sub s minus rho sub f times g divided by 9 eta. Substituting our values, v sub t equals 2 times 0.001 meters, squared times 7,800 minus 1260 kilograms per cubic meter times 9.8 meters per second squared, divided by 9 times 1.4 Pascal seconds. Computing this gives us v sub t equals 0.0102 meters per second, or about 1 centimeter per second. Stokes' law and terminal velocity have many important applications. In medicine, they help understand how aerosol particles in inhalers reach the lungs. In environmental science, they explain how pollutants settle in water and air. In industry, They're crucial for designing processes involving particle sedimentation. Remember that our formula assumes a laminar flow regime with low Reynolds numbers. For larger objects or higher speeds, more complex drag equations are needed. Let's summarize what we've learned today. Stokes' law gives us the drag force on a small sphere moving through a viscous fluid. Terminal velocity is reached when the weight, buoyant force, and drag force balance out, resulting in zero net force and constant velocity. The formula for terminal velocity, including the buoyant force, is V sub t equals 2 r squared times rho sub s minus rho sub f times g divided by 9 eta. This equation is important in many scientific and engineering applications. Thank you for watching. I hope this has helped you understand Stokes' law and terminal velocity.